Hey Year 11s. In this video, I'll be going through all the examples just before exercise 3b, sketching functions. Make sure you refer to your lesson notes, and if you're looking for a specific example, just skip ahead in the video. Work example 3.8, use technology to sketch y equals x take 3 over x plus 4, labeling all axis intercepts and asymptotes. Alright, so let's bring up our calculator and let's graph this function. So we had x take 3 over x plus 4. So let's graph that. Okay, so let's just zoom out a bit. So let's just go into window settings. You can also just press zoom out, but I'm just going to set this manually. Let's say we go to x-min maybe 15 and y maybe 10. I'm just doing this based on what I see. I just want to see more of the graph. Alright, move this around a little bit. There we go. Alright, so we want to label all intercepts and asymptotes. Alright, so we can use the calculator to help us find the intercepts. So I'm going to go into Analyze Graph 0. Alright, we have, so 0 are just your x-intercepts or your roots. So we have 1 at 3, 0. And then if I go into traced, if I want to find my y-intercept, that's when x equals 0. So we have 0, negative 0.75, so it's negative 3/4. There's our y-intercept. So let me just go ahead and clip that in. There we go. Okay, and then we've labeled the x and y intercepts. Alright, and we're going to now have a look at the asymptotes. We can see where they are visually, but we can also confirm that by doing some calculations, so we're going to do that as well. Alright, so we can see that it looks like there's an asymptote at, let's get the ruler out. Let me just draw a straight line just to make it easier. Alright, so it looks like we've got an asymptote at x equals negative 4. And then also, looks like we have an asymptote at y equals 1. Alright, so let's confirm this. So the domain, if we look at x take 3 over x plus 4, that just means our domain is x cannot equal negative 4 for our domain. Alright, it can take on any other real numbers. Alright, because we cannot divide by 0. So that's why we have an asymptote at x equals negative 4. And then let's have a look at the range. Okay, let's sub in 1 and see what happens. So it appears that y cannot equal 1. So let's test that. 1 equals x take 3 over x take 4. Alright, multiply both sides by x take 4. And if we arrange this, we get 0 equals 1. But that can't happen, so no solutions. Alright, so we can justify why there's an asymptote at y equals 1 as well, and that answers the question. Example 3.9, find the minimum value of f of x equals x e to the x, hence find the range of the function. Alright, so let's graph this one as well. So let's hide our first one and graph our second function. We want x. Need to press the right button for e to the x. There we go. Alright, I'd just like to zoom in a little bit, so let's just zoom in here. Oh, maybe too far. Zoom out a little bit. There we go, that's fine. Okay. So we want to find the minimum value, so let's get the calculator to help us do that. So analyze graph, minimum. We see the minimums here somewhere, so here we go. Right, we have -1, -0.368. Let's clip that. Into our graph. Alright, so from the graph, our minimum value is -0.368. Therefore, our range is anything greater than and including -0.368, and we can see that on the graph. 3.10. Find the coordinates of the vertices on the graph f of x equals blah blah blah, and then given that the curve has a line of symmetry, find its equation. Alright, so let's graph this. X to the 4, take 4x cubed plus 2x squared. I may have done this already. Yes, I have, and I've already labeled it all. Great. So let's pop this in here. So we can see that the vertices are the following. I've labeled them, so just go into Tools, Analyze Graph, Max and Min. Alright, that's what vertices mean. And use the calculator to help you find them. And then B, it has a line of symmetry, so if I use red, alright, we just have to do this visually. Alright, we can see that we have a line of symmetry here. Whoop. You get what I mean. That might be better. Alright, there's our line of symmetry. The equation of that line, well, it's a vertical line, it passes through 1, 0, so x equals 1, and we're done. 3.11. Sketch a graph with the following properties. Okay, so that's when we have to, I'm going to do my best to sketch it on here using my trusty ruler. So let's just draw up our axes. So we want just trying to make it neat. There we go. Alright, there's our axes. Well, let's call it f of x because that's what we've been given in the question. So the range is less than or equal to 0 and greater than 1. There are vertical asymptotes at x equals plus or minus 2. The only axis intercept is the origin, which is also a vertex. Okay. Best way to approach this one is by putting the asymptotes in. Let's put the asymptotes in. So plus or minus 2. Alright, let me use a scale of 1 here. So every square is 1. Alright, so there's my asymptotes. There's one there. It's a bit tricky trying to draw this on the computer, so bear with me. Alright, there's my two asymptotes. The only intercept on the axes is the origin, so let's put a point there. So it's gonna pass through that point, and it's also a vertex, so aka turning point. And let's see. Alright, so f of x can equal 0, but it can't equal 1. So that means anything, so including 0, from 0 to 1, alright, we shouldn't have anything there. Alright, so it's almost like I'm going to put another asymptote here, right? Because our graph is not going to equal 1, so it's not going to touch that horizontal line either. Okay, so that means if our point here is a vertex, well, the only way it can go is something like this. Alright? Because if the function doesn't exist from 0 to 1 in that little section there, then our graph can only have, well, this vertex can only be a maximum. The range, okay, vertical asymptotes at plus or minus 2. So we've got our asymptotes. Now, since this is a function, right, well, we can't have anything in this section either, in yellow there, because then it wouldn't pass the vertical line test. It wouldn't be a one-to-one or many-to-one function. All right, and so if there was anything else in there, then it wouldn't be a function. So that means the only way our graph can go is something like this. Alright, so you'll see that the graph will approach those two asymptotes, but they will never touch them. Okay, and there we go. Point 12. Okay, this one's an interesting one too, so I'll do my best to make sense of it for you. So this time we have just a contextual bit of information, and we're going to try to sketch or model this situation. We don't have an equation. We've just been given values, and we're going to try to put it into a graph. Okay, the function n of d gives the total number of seeds distributed within distance d of the center of the tree. The tree is modeled as a cylinder of radius 0.2 meters. The tree releases a total of 300 seeds. There are only 50 seeds within 1 meter of the tree, and half are distributed more than 3 meters from the tree. This one is actually quite tricky, particularly if you haven't done a lot of functions before. Even if you have, it's kind of a strange one too. Well, that's just what I think. Okay, so I'm going to draw my axes, and then I'm going to draw another little diagram to kind of explain what we're trying to model here. So here, and so just have a think about that as I do this. Alright, so here's my my x-axis is going to be d, and my y-axis is n of d. So n of d stands for the number of seeds. So basically, if I try to draw this, there's my beautiful tree. Okay, it says, well, the trunk, it says it's a cylinder, so let me do that. It says it's got a radius of 0.2 meters, and just imagine that, you know, it's going to drop, like seeds are going to fall from the tree onto the ground or whatever. And it says the tree releases a total of 300 seeds. D is the total number of seeds distributed within distance d of the center of the tree. So whatever distance that is, that's d there. And the tree releases a total of 300 seeds. There are only 50 seeds within 1 meter, and half are distributed more than 3 meters from the tree. Okay, so I'm going to make my y-axis go to 300. Or I'm going to use a scale of 50 for every box square. Alright, 300 because the tree releases a total of 300 seeds. Now on my x-axis, I might just use a scale of 1, so 1, so D is in meters, and number of seeds. Okay, blah, 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 blah. Okay, hopefully that makes sense so far. Right, now let's try to put some points onto this graph for this situation. So let me just write that better. So that's 0.2 meters. Okay, so if it's got a radius of 0.2 meters, that means there can't be any seeds from 0 to 0.2 meters. Okay, because that would be like inside the trunk or the tree, and obviously the seeds are going to fall away from the tree. So that means it's going to start, so that means let's find 0.2. 0.2. Let's say 0.2 is here somewhere. That's where it's actually going to start. That's our first point there. And then there are 50 seeds within 1 meter of the tree. So within 1 meter, there's going to be 50 seeds. So we're going to have a point there. And half are distributed more than 3 meters from the tree. So that means also that half are within 3 meters of the tree. So when d equals 3, we're going to have half of the total, half of 300, which is 150 here. And that's our next point. And right now, if we now, this is where it kind of gets a bit, we kind of just have to interpret it however we think. Using the fact that the tree releases a total of 300 seeds, I think there's probably more than one way you can do this, but I'll just do it this way for this example. So we know that, we don't know, after 3 meters, we don't know how the seeds are going to be distributed, right? But we know that eventually the tree is going to release a total of 300. So the graph is going to hit 300 eventually. We just don't know when, right? That's from the information we got. So right now, if we just draw something like this and make it approach, whoops, let me do it better. And just make it keep going up. I'm trying to put a little bit of a curve in there. This is not meant to be a straight line. Alright, but I don't think we should treat 300 as an asymptote either, because it should hit 300, right? Because that's what we've been told. Okay, so just make your graph. Eventually, it's going to reach 300, and then we'll just stop it there. Okay, hopefully that makes sense to you. Okay, 3.13. Finding the intersections of graphs using technology. Okay, find the points of intersection of x cubed take x squared and 2x minus 1. Right, let's graph this. So x cubed take x squared and 2x minus 1. Let's just open a new document, graph. Okay, so we have x cubed take x squared, graph that. And then we also have, what was it? 2x take 1. Okay, there we go. And we're trying to find the points of intersection. That means when the two graphs, all the points where the graphs touch each other. So I can see that I have 3 intersections. So let's just get the calculator to find them for us. So analyze graph, intersection. Alright, let's just work from left to right. There's one. Let's do it again. Intersection. There's another one. And there's our third one. It's a little bit messy, but we have all our points now. So let's just clip this in and answer the question. Alright, so our intersections are, well, they're on the screen, so there's no need for me to rewrite it. Alright, done. 3.14, find the zeros of the function. Okay, so zeros means x-intercepts, which is the same as saying the root of the function. We're going to, again, use the calculator to help us do that. So let's graph it. 1 over x plus x, take root x, take 2. So let's graph that. Whoops. So we have 1 over x plus x take square root x take 2. Alright, there's our function there. Alright, we don't really need to do any zooming in or out, so let's just go straight to Tools, Analyze Graph, 0. Alright, we see that there's 2 intercepts, so I'm going to click just before the first one, just after. Alright, that gives me my first 0. And then let's just do the same for the next one. So nice and easy. There we go. There's our zeros. Okay, I have got this somewhere already. Yep. Save me the clipping. Whoop, it's a big diagram. Alright, and then you just write out your points. Alright, but that's essentially 3.14 done. Final example of this chapter. Hooray, can't wait. 3.15, find the roots of this equation. Okay, so if you want to find the roots, or the zeros or the x-intercepts of something like this, you just want to rearrange the function or equation so that one side equals 0. So essentially you turn x squared take e to the x, that's your function, and you've let it equal 0, and now you can find out where it touches the x-axis. Alright, so let's just do this on the calculator. So we have x squared take, remember to press the right button for E, otherwise you're not going to get the proper graph or a graph. And then we just go 0. There we go, negative 0.703 and 0. Let's clip that. Whoop. And there's our 0. Alright, and just write out the coordinate. Alright, so that's all the examples from chapter 3 now. So now you can do all the set questions in 3B as well. So make sure you invest a bit of time into this, particularly if this is new to you and you're finding this a bit tricky. Alright, so spend some time practicing because this is one of the most important topics we'll be doing going forward. Alright, have a good one, and I'll see you soon.